Well, this is lecture number 10. Okay, we will start discussing a topic called waveguide. And we've been talking about plane waves in infinite extent. So all this region consists of all space. But today, in this topic, we'll talk about instrumental waves inside a container, some sort of container, some kind of structure. And that structure is used to guide the flow of the instrumental waves, hence the name waveguide. And the physics of waveguide is used in the research of radar. In the radar station, microwaves generated in resonant cavity traveled through a waveguide to a horn antenna, from which the waves emerge into free space to be scattered by detected objects. Well, maybe like an enemy plane or something like this. And my late thesis advisor, Julian Schwinger, in fact, spent his wartime doing research on radar, on waveguide, at the famous, MIT's famous radiation laboratory. And there he honed his mathematical skills, which I will talk a little bit later on in this lecture. All right? So waveguide. So let's say that we have a waveguide made up of conductor. So there's some thickness. It's a conductor. It's a conductor. And let's make the coordinate system like that. Z, X, Y, X, Y, right hand coordinate, X, Y, Z. And this extends all the way to infinity, let's say a long pipe, hollow pipe. So this cavity, inside this hollowed conducting pipe, is the region that the instrumental waves would travel, say, along the X direction. And so let's talk about, so inside this pipe is free space, so that we will have to make use of Maxwell's equations in free space without sources, without putting rho equals 0, J equals 0. What about boundary conditions? So we're going to solve the Maxwell's equations without sources, inside the pipe, and the boundary condition, namely on the inner surface of this pipe. What are the boundary conditions? Well, you remember that each of the Maxwell's equations give rise to one boundary condition. This tube, in general, involves charges and currents. Since we do not know, the surface charge, the surface current on the surface, so let's not use the boundary conditions coming from these two equations. But from this equation, we know the boundary condition says that the parent component of the electric field E is continuous across the surface, across the boundary. And from this equation, we know that the perpendicular component of magnetic field B is continuous across the boundary. So we will make use of this boundary condition as well as this boundary condition. All right? So we're interested in, instrumental waves, E and B, complex. That is given by the magnitude E to the I, let's say that travels along the X direction. Wave number K, X minus frequency omega T. And similarly, this B is given by the same exponential function and with amplitude B naught to the e to I k x minus omega t T. Now, okay, let me write down it, okay, amplitudes. And okay, let's follow the notations used by Griffiths. Okay, the amplitude for the electric field E is okay, E not twiddle. There's three components. Okay, I, J, K. This is the X component. So E, normally I would call this E not X, but I'm going to suppress the zero, the not, okay, just for convenience. So that's E X, okay, of, and let me also omit the twiddle. Plus, okay, B E Y as a function of something, plus E Z and something. Okay. And similarly, B not twiddle is okay, B X depending on something, I's component, plus B Y depending on the argument, J okay, plus E B Z K. Now, since the waves okay, propagates along this pipe, okay, so that obviously there will be Y and Z coordinate dependence, so that okay, those okay, components of E and B okay, depends on Y and Z, 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 Y and Z. Now, at this point, you may say, Dr. Ng, you have forgotten okay, the okay, X component, the longitudinal components of the electromagnetic wave okay, propagated in okay, this in vacuum okay, should vanish since we expect the electromagnetic waves to be a transverse wave. That is true for the case of infinite extent. But since space is confined, the waves are confined inside a certain region, so in fact, okay, the waves are no longer transverse, as okay, we will show. Okay. In fact, the boundary conditions okay, that we are going to use will show you that okay, the X component okay, got to be there. So there's, okay, notice this, that's been the exclamation. All right, so all the X dependence appears in the exponential functions, and each of the okay, different components of E and B field okay, depends on okay, the transverse okay, coordinate Y and Z. All right, the boundary condition, as I said, okay, is okay, the following. Okay. E being continuous, since inside conductor, the electric field E is 0. So the obviously the parallel component of E is also 0. So that means that the boundary condition, okay, on the boundary would be okay, E parallel is 0. Next, okay, what about the boundary condition? Okay, here, this one. Well, E is equal to 0 inside conductor, and we know, okay, from Faraday's law, that okay, curve E is del B by del T. If E is 0, then the left hand is 0. Then that means that del B by del T is 0. And if the magnetic field B started with 0 value, it remained 0. So let's adopt that. So let us okay, use okay, for the second boundary condition, name the B. Let me use go for consistency. Use green pen here. So B perpendicular being 0 on the surface of the inner pipe. All right? Okay, so now we are ready. So we have, okay, have to solve the Maxwell's equations for these waves subject to these two boundary conditions. All right, now we have to do quite a bit of algebra. And let me start. Okay, I'll give you careful. Make sure that you can see. Okay, you see. Let me use this and this equation. All right. From the first equation, the curl of E being equal to minus del B by del T. Do I want to, maybe in fact, I should use sliding board because I will have to use, maybe here. Let me use this. A sliding board. So I'm interested in the equation curve E is equal to minus del B by del T. Okay, so I will work out the x component of this equation, y component of this equation, and z component of this equation. X component of this equation. So obviously, it's a curve. Okay, I draw this x, y, z. So this one, okay, will be del by the x component. So del by del y, okay, e, z, minus del by del z, e, let's see, y. And that's equal to minus, okay, x component del bx by del t. Okay. In fact, let's be careful. Let me complexify this whole thing. So, like this. Okay. So what's that? Okay. On the left-hand side, on the right-hand side rather, okay, I will have, okay, del by del t, okay, equal b, del t will bring down a factor of minus I omega. So it's minus I omega, okay, and then, okay, the x component of b, so bx, times the exponential function, which of course is also present on the left-hand side, so they will cancel between the two sides. How about this one? Okay, del, okay, Ez by del y. Well, okay, Ez depends on y and z, so that is such a term. So that gives me del by del y E Z. This is EZ. I will now drop the twiddle and drop the knot. Okay. And then minus, okay, del by del Z actors on this. So del by del Z, okay, E Y. So this is, okay, this is the equation. All right. Next, let me take a look at the y equation. Okay. So that obviously, okay, y. So I have del by del z acting on ex minus, okay, del one del by del x, okay, y. I mean e z. That would be equal to, okay, the y component, that would be equal to, okay, minus del b, okay, y by del t. Okay? Have I done it correctly? Y component by Z, correct, Y, right. Okay, again, the right side gives me, okay, delta, so minus I omega, okay, coming from derivative of the exponential function. Okay. And then I will have, okay, By. And thus, okay, x component, all right. And this is del, okay. So del by del Z E x. And then this equation, derivative of Z E, okay, by del x. But del x, of course, okay, x on this one, but there's no dependence on in the amplitude and along Z component. On the other hand, there is dependence of x that appears in the exponential function. So that breaks down a factor ik. So minus ik times yes, E Z. Similarly, you can do the same thing for y. Okay. I leave the exercise for you to show that. Okay. This gives rise to minus del by del y E x. Okay. Minus plus I k E y is equal to minus I omega B Z. And can make sure that I've done the algebra correctly. Let me take a look in my notes. Because it's important for me to get the equations right, otherwise the whole thing will be wrong. Yeah. All right? Yes. Oh, right away, there is a mistake here, the sign. What's wrong with the sign? Oh! This minus sign. I can't forget it. Good thing that I to look at the notes. Okay. Open plus. And then continue. This one. Minus IK is yes. Okay. This one. Nope. There is. Okay. Okay. IKEY minus. Correct. That was the only mistake I made. I forgot about this minus sign on the right side. All right? So I've made use of this equation. The third Maxwell's equation. The furthest law. Let me take a look at this equation and do a similar thing. Actually, we do not have to do that. If you recall that these two equations are related by duality transformation. Everywhere I see E, all I have to do is replace it by CB. Everywhere I see B, replace it by minus E over C. And you remember that? Okay. Also, C. Here. The square root of epsilon naught mu naught is the reciprocal of C. All right. So that all I have to do now is to use the equations that I have from this equation, and now right away write rid off the equations coming from the last Maxwell's equation, namely the Ampere-Maxwell equation. So here, let me put del by del y goes, so that E goes into B, so I have del by del y, B, Z, minus del by del z by, and that's equal to, okay, e goes to this, okay, with b goes to minus, okay, e x, and then, of course, to be, okay, correct, so b, this, so this divided by c squared. All right, and similarly, I can write down the equation, the dual equation. This will give me del by del z bx minus I k b z is equal to minus I omega over c squared. This sums. Okay. This is minus. Oh, minus is good. Sorry. I've written it down correct. Here's this plus. That's right. I can't forget this minus. So it's correct. Okay. Let's see. B goes into minus E like this. And then from this equation, okay, take the other transformation, I will get minus del by del y, E goes into B, plus I k, E goes into B, E y, and this equal to B goes into minus, this I was affected square c squared downstairs. B equals to minus, okay, E dot. And again, okay, just to make sure that I've copied things correctly, let me check. And this, x and this is the other x minus x. Correct. I just want to make sure that I've copied down the things correctly. Otherwise, we'll be making, okay, the mistakes will multiply rapidly. Okay. So we'll make use of the last two Maxwell's equations to arrive at, okay, this, and now I can erase this. So those are the equations I can. And with a little bit of, okay, hindsight, let me rewrite the last equation here, okay, right beneath the second equation, this one. So that, okay, let me put this to the other side, and this goes to the other side, this goes to the other side, okay, would be, this goes to the other side, would be minus I k e y. So this goes here. And this goes to the other side, becomes minus I k b z. Okay. And this one, okay, stays, okay, let's see. Stays on this side. So minus del by del y, okay, e x. Let me at this point separate these two top equations from the four equations below this line. Okay. And notice that we have x, y, z component dependence very clearly written down there. Okay. What I would like to do at this point is to, in fact, okay, write, okay, the y and z components of E and B in terms of the x components of E and B. So we have four quantities to written in terms of two quantities. And okay, we need four equations. These are the four equations. Okay, that's okay. Oh, I forgot the rest. All right, continue. And let me now do this. Let me take a look at these two equations. That's a PZ dependence, PZ dependence. Okay. EY depends, EY dependence. So that if I multiply, okay, this equation, okay, by, oh, that's the move, other one. This sum, I think, there's something, did I miscopy something? Yes. This is not correct. Oh, omega, no wonder, see? Okay. Mistakes. It's omega. Is that correct now? I thought I checked the equations. But not that one, I guess. Okay, and since okay, all the three terms got minus sign, so I may as well change up to plus sign. Let me multiply this equation by omega, and this equation by k, and add them up. Then look at the BZ term. Then this term will be minus I k omega BZ with the minus I. Then this becomes plus I k omega BZ, the same except for sign. So now let's add the two equations. All right? So that I would get, let's say, okay, let me write this, okay, let me do slowly, otherwise I will make mistakes again. This plus that with omega, so that is, okay, let me write this, put this on the left hand side, okay, so this would be, okay, minus I omega squared over c squared times EY is this term, plus this, plus I k squared, that's it, plus I k squared times EY, and that's equal to this, and by construction, this term cancels this term, so I'm left with this, so now I have omega del bx by del z k, so plus k del by del y e x. And and from that, let me take a look at how come it doesn't give me the thing? This, all right, okay. So that's it, okay. And so the EY would be equal to this, divide out, so let me put this, divide out will be minus I, will be put I here, divided by omega squared over k c squared, and I put this to the other side, so minus k squared, right, is equal to the other side, so times this omega del bx by del z plus k del by del y ln ex. And let me check, since I've been making mistakes, so that my EY is I this omega bx okay del z okay, plus k del ez by del correct. Okay. So we can be able to write down EY as the x component of E and B in terms of derivatives. So I want to put the y and z component E and B in terms of the x components of E and B. I've done it for EY. Okay. We do the same thing with other equations. Okay. And let me write down the expression for EZ. That will be equal to the same factor okay, here where y goes into z and z goes into minus y minus del bx by del y goes into z plus k del ex by del z. Exercise. So here we get this same factor standing in front of this two terms. And y equals to z equals to minus y equals, I think I got it. And then, of course, you can solve for by and bc, but we don't have to do it. All we have to do is to take these equations and make derivative transformation. So we have, let me write down these two equations. This one, E goes into B. Is equal to this. I'm looking at this one. B goes into minus E, so minus omega del E x by del z. Okay, but divided by c squared. And then this one, E goes into plus B, so plus k del E x. E goes into B. Ex, okay, del y. And E equals, so what do I have? Like this. Aside from a factor of C, but before that, let me check the others. Remember, By is equal to same thing, and K del by del is this one, and this one's minus the Ex, correct. Amazing. If I'm all right. Finally, the equation for the z component of B. A lot of algebra, but you have to do the algebra correctly. Same factor, okay? Y goes to z goes into minus y, so it's plus omega over c squared del Ex by del y goes into z plus k del Bx by del z. I think that's it. Again, check always to make sure I'm correct. Bz equals omega c squared del Ex by del y plus k del Bx by del. Correct. All right. So we have now 4 equations. Okay. For the y and z component of E and B in terms of the x components of E and B. Okay. So let me draw a line here. So these are the 4 equations. And at this point, let me see. Okay, let me take a look at the bottom 2 equations. Right. And let's see. Oop. Okay. Multiply, act on this equation by del z and act on this bottom equation by del y. In that case, look, in that case, and I want this del z, and I want one of them minus. Let me got to be minus. So maybe let me put minus on here. So as far as this term is concerned, after del by del z act on it, then I have both del by del z, del y act on bx. And for this equation, I will have del by del y, del by del z act on kx, but with a plus sign. So if we add the two up, this cancels. So that I'll be able to write down this, and let me do that. Let me do it here. All the way here. Yeah? So I have, on the left hand side, I have minus del by del z act on by, plus del by del y act on bz on the left hand side. And the right hand side, as I said, by construction, these two cancels, so that I'm left with del by del x, with this factor, I divided by omega squared over c squared minus k squared. Now this is with a minus sign, so minus is plus, and omega c squared over c squared, del by, as I said, del by, del z, minus plus, so del squared by del z squared, and then this term, del by del y, with a plus sign, so plus, same factor omega over k, so plus del squared by del y squared acting on ex. All right. Well, doesn't have much, does it? Except now, let me take a look at the left hand side. Left hand side involves this del by del y act on bz minus del by del z act on by. So this combination, using this equation, is equal to minus I omega over c squared x. Now, we only have ex component in the whole equation. So what's that? And also this factor cancel with this factor. I cancel with I. So that I get the following, namely that I have del squared by del y squared plus del squared by del z squared, and this goes to that, put the other side, there's plus omega squared over c squared minus k squared acting on ex, which depends upon y and z equals 0. So now, I have second order differential equation for the x component of E. Now, by now, you know, you should do the same thing for the bx component. But that's easy. All you have to do is use duality transformation. E goes into CB. C cancels out. So that I have this bx, y, z. Two equations. two identical differential equations of second order. And once we have, of course, we have to solve these two equations subject to the boundary conditions. You remember? Subject to the boundary conditions. Once we have solved for Ex, Bx, then of course you will be able to work to rid off the y and z components of E and B. So the problem is done. So it boils down to solving a second order differential equation. So the equations we want to solve will be these two. Somehow erase some. Okay, so these are two equations. Before I give an example, and to solve those two equations, let me make one remark and one important observation. The one remark is the following, namely that for waveguides, we can in fact put all the solutions into three categories. First category is transverse electric wave. So it's TE wave. Transverse electric. The other category consists of solutions involving transverse magnetic. Did I use TB or TM? TM. Transverse, this stands for transverse. That means transverse electric field. That means that for this case, we have Ex is equal to 0. And for the transverse magnetic wave, obviously, that means, Bx is 0. And there's a third category, is transverse EM wave. So that means both Bx and Ex is 0. And I will state without proof, because it's too complicated, that it turns out that all solutions can be written as linear combination of these three types of waves. So these are PHYS for us to consider transverse wave, transverse magnetic wave, and transverse electric and magnetic wave. That's remark number one. That's the remark. And now the observation. Let me say a few words about TEM wave. So the both Ex and Bx being 0. Now it turns out that claim. If we consider a hollow pipe as the waveguide, so in this waveguide, there's only one region. So the pipe is hollow. It turns out that there can be no TEM, wave for a hollow waveguide. I underline the word hollow here. If you construct the waveguide such that there's another tube inside this big tube, then that is no longer true. Then there can be non-trivial TEM wave. But let me prove this claim. The proof is well, it's not difficult, but it is illustrative. It's interesting. It involves something that you learned last semester. All right. So let's consider the TEM wave. So that for this wave, Ex is equal to 0, and as well as Bx is equal to 0. All right? And now, let me take a look. Ex equals 0. Oh, where am I? Oh, Maxwell's equations. Oh, maybe I can do the proof here. Let me prove the claim. Proof. Ax equals 0. Bx equals 0. Ex equals 0 means then that is, so let me start with the first Maxwell's equation with the right side being 0. So this diverges E being 0. E here, of course, I'm interested in the and I can erase other. Oh gosh. Oh, here. Let me see where I can. Okay. Okay, so Ex is 0, so this is 0. So that I have only left, here I've only left with del by del y, Ey. And then plus del by del z, Ez equals 0. Okay. All right. And so that, this vector, B E naught, E naught, this is here, this is now obey, this to obey this equation constraint, so that in fact E naught is divergenceless. Okay. Next, let me make use of Bx equals 0 condition. And where do I see? Okay, Bx is equal to, so that, remember this equation. Now let's make use of this equation. Bx is 0, so the right side is 0, so that I have del, let me copy, del Ez by del y minus del by del z acted on by, that's 0, coming from this equation. With understanding that we are talking about transverse electric magnetic. So transverse magnetic means this is 0. So that this is 0. Okay. So now let me take a look at curl of E naught. Let me already we see that the x component of this is correct. So this this equation is the x component of this curless condition. Take the x component, I draw this x, y, z clockwise. The x component of this is del by del y okay, acting on EZ minus 1Z interchange. Now I have to take a look at the Y component and the Z component. I just do the Y component of this. Y component of this, okay, would be Y component of this. Y component of this would be del by del Z acting on EX minus del by del. So Y component del by del Z. So del by, okay, del by del X acting on EZ. And what's that? Oh, too fast. What's that? Okay, this, okay, we said is 0 because okay, we are talking about okay, EX is 0 and BX is 0, so this is 0. And what about this one? Okay, del EZ by del X. So derivative of the Z component of E with respect to X. But just note okay, X dependence in the Z component of the amplitude. So this is also 0. So this is 0. So that okay, we've shown that X component of the curve is 0. Now we've shown the Y component is 0. You can do the same thing for the Z component is 0. So in short, in fact, okay, not only is okay, E naught divergenceless, okay, but E naught is also curveless. So this too. So okay, for okay, TEM wave, okay, the amplitude of the electric field E, okay, for those components are both divergenceless and curveless. What does that mean? All right, let me take a look. Since E naught is curveless, that means that in fact E naught can be written in terms of the gradient of a scalar called V minus. Just call it V minus V. This condition. And now, okay, we also know that E naught is divergenceless. So divergence of this equation could give me the Laplacian. So that means Laplacian acting on V is 0. So that the E naught, okay, the components of E naught, okay, E naught amplitude of the electric field E can be written as gradient of a potential, and that potential obeys the Laplace equation. Now you may recall from your knowledge from something that you learned last semester, okay, 311. Okay. That okay, solution to Laplace equation has no local minimum and no local maximum. The local maximum and local minimum being reside on the boundary. Minimum as well as maximum, okay, reside on boundary. On boundary. So the maximum of V and the minimum of V reside on boundary. Okay, and we are talking about okay, the boundary being, of course, the inner surface of okay, the pipe. But on the inner surface of the pipe, we know okay, this boundary condition, namely that the parallel component of E being 0. That means that the inner surface of the pipe is an equipotential surface. That's a condition, doesn't it? And this is the boundary for this region, this hollow pipe. That means that the maximum value of V is take place on the surface, on this equipotential surface, and it's minimum also. But since the potential is equal everywhere on the surface, that means that both maximum and minimum value of that constant potential take place on the surface. Both minimum and maximum being the same value of the potential on the surface. That means maximum value is equal to the minimum value. And that means the potential V is constant in the pipe. Constant V in the pipe means that, the electric field E is zero. So there's no wave propagating at all. Hence, they claim that for hollow pipe, there can be no TEM wave. I hope you appreciate the argument. It's non-trivial, actually, if you think about it. You have to make the right argument at the right time. Otherwise, you're all confused. I hope you appreciate the intricacy of this argument. But that's done. Next, what should we do? And next, what I would like to do is the following. We will be talking about a certain hollow pipe. And of course, since I can not have the TEM wave, so we can have TE wave or TM wave. And for the example that I'm going to give, let us look for TE wave solution. And all right, so all I have to do now is where's my second order differential equations? Oh, behind. Oh, here! Oh, erased. Gosh, this is like this. There, y squared, L, z squared, over c squared. So that we're interested in TE wave, that means EX is 0, so that I want to solve the second equation, since I've erased this. So I want to solve the BX. Equals 0. So I want to solve this second order differential equation. To look for transverse electric wave in the hollow pipe, which takes on the form of a rectangular pipe. So let me, I think I can erase all this now. Yes. Oh, I have to remember the boundary condition. B perpendicular boundary condition. Okay, still here. Let me put square box on it. Keep. I will have to make use of the boundary conditions. And the example is the following. Let's talk about a rectangular pipe. So that I can use Cartesian coordinates and the differential equation will be easy to solve. We have been using differential Cartesian coordinates anyway. So, so this being conductor, conductor. And let's say that, let me adopt the coordinate system with the origin at the bottom here. is the x direction, x, y, so this y, this z. And let's say that, okay, this is original coordinate system, this is, okay, the top part, okay, correspond to y equals a. Okay, and this, okay, the vertical plane, vertical line, on the inner surface of this rectangular pipe correspond to z equals b. So 0 to b, 0 a, right, for the z and b coordinates respectively. Let me finish this up. All right. And I want to solve this differential equation. Okay. One method that presents itself is, okay, the method of separation of variables. So that, let me write, okay, bx, the x component b as function of y and z, as part of two functions. Okay, so bx of y and z, let me write it as, okay, y function of the coordinate y, z function of the coordinate z. And let's substitute this yz into this equation. So that we will get del by del y squared acting on the y as a function of z as y, and this term will leave this factor untouched, so z, and plus similar this one, y del by del z squared acting on z is a function of z. Okay. Then plus constants omega squared over c squared minus with number square of z b is y z 0. That's the equation I'm going to solve. Substitute, okay, for this boundary condition. All right, and I can, since y depends only on y coordinates, I can change the partial derivatives into ordinary derivatives. So it's d. Similarly here, d squared by dy squared, d squared by dz squared times z. And now let's remember that y depends on the y coordinate, z depends on the z coordinate. So that this, before I do that, so let me divide out the whole equation by yz. Divide by yz. Then of course, the first term becomes 1 over y, d squared big Y by d small y squared, plus this one, 1 over z, d squared z by d e squared, plus this constant, this divided out already, omega squared over c squared minus k squared. This is 0. This term can only depend upon y coordinates, and this term can only depend upon z coordinates. And that's true for arbitrary y and z. How can it be possible? This depends on y, this depends on z. How can things be add up to be such that that's true? The only way that can be true is that this term has as well as this term, in fact, are constant. So let me call this to be minus k y squared. And I use minus for good reason, as you see. So that I can satisfy the bound condition. Similarly, I call this is a constant given by minus k z squared. All right. So now that, and let's see, I can now use this side of that part. So that means that for this, okay, I have okay, d square y by dy square okay, is equal to minus a constant which I call ky squared times y, which depends only on y coordinate. The second order differential equation, so there are two solutions. Write them in terms of cosine and sine function. So that means that okay, y of this is equal to, let's say, b, okay, I can use ab, a, okay, sine, okay, of k, y plus b of cosine k, y. And now it's time okay, to impose the boundary condition. I hope I did not erase that. Oh, please. Oh, still here. Oh, scared me. Okay. Now we want to impose the boundary condition. Okay. The perpendicular component of B on the surface has been 0. So let me take a look on this surface. Okay. There was on the line here inside this box. So that the perpendicular component of B, of course, points along the y direction. So that we want B y is equals 0 at y equals a. And similarly, okay, the perpendicular component okay, on the bottom okay, in the surface is such that this okay, by is 0 at y equals 0. Oops. So by is 0 on the surface at y equals a, and by is 0 at y equals 0. All right? Good? Now, let me take a look at by equals 0 at a first. All right? And where are we? Okay. So we want at okay, y equals a, okay, by, well, by is, okay, by equals 0. And then, okay, I consider the case that y equals 0, by is also equals 0. What does it mean? Okay, that y equals a and y equals a, by 0. You said, well, what's by? We've been solving for bx, right? We've been solving for bx. The equation is for bx. This by is nowhere in sight. Ah, you forgot it. And I've been smart enough to keep the equations here. All right? By is equals 0. By is here. Okay? And that's 0 at okay, y equals 0, and y equals a, let's say. All right? Let's see. This is 0, so that okay, this is 0, but we're talking about okay, transverse electric okay, wave for which Ex is 0. So that in fact, okay, we have to impose the condition that del B by del X by dy is 0. So this implies that okay, del Bx by del Y equals 0 at y equals 0, and similar at y equals, and y equals a as well as y equals 0. All right? So Bx, okay, is okay, given as product of big Y and big Z. So that since we are talking about derivative with respect to Y, so we want in fact this y of y at a y is a is 0, and similarly at y equals 0 is 0. All right? Oh, I'm sorry. Not yet, no, not yet. I want the derivative, sorry, of that pencil. Okay, very quickly. So y is 0, y is a, derivative of bx with respect to y is 0. Okay, of course, this is the part that we're interested in bx. So derivative of this, sine goes into cosine. Cosine goes into, forget about factors, or minus sign or something like that. Goes into sine of k, y, y. It's 0, and a, y is a, and y equals, let me do this, and y equals 0 first. And y equals 0, let me do this first. If y equals 0, this is 0, but this is constant, not 0. And it's multiplied by a, but the whole thing is 0. So that right away, I come to the conclusion that this term is not there. Next, what about at y equals a, this at y equals a, this has to be 0. That means sine of k y a has to be 0. That means that k y a has to be multiple of pi. Let me call this m shape integer of pi. And since this involves cosine function only, which is even, so that it suffices for me to keep non-negative integers. So m is 0, 1, 2, etc. And similarly, you can take a look at the z factor in this wave, big, this one. Impose the condition on the condition that BZ 0 on this vertical line, and also so the bound condition would be BZ equals 0 at Z equals 0, as well as Z equals B. You do the same thing, so that now we know that y will be just given by certain, let's say cos C of cosine kyy. Ky can only take a value of m pi divided by a. Okay, I'll be done in a moment. Y times cosine of n pi over b z. Okay. And let's stop here and continue in next lecture.